Hey, hello there. So today I'm talking about this rather classic question number 4, median of two sorted arrays. We have two sorted arrays, nums1 and nums2, each of size m and n respectively. We need to find the median of this two sorted array as if they were combined. So we're looking at the median number for the m plus n elements together. So record the median is basically a number that we can use to partition the sequence into two halves, equal size two halves, where the first half is a number that's smaller than or equal to the median. The larger half are the elements that's larger than or equal to the median value. So that number, based on whether it's even number of elements or odd number of elements, that calculation is slightly different. If we have odd number of elements, we just take the middle one if it's in a sorted order. And if it's an even number of elements, we take the middle two from the sorted order and take the average. That's how median is calculated, and the partition that the median value creates. So that's the property of median value. And it's basically a 50 percentile. So you've got half of the number in one side and another half in the other side. So this question asks us to write an algorithm that's in log time. So just recall how I was describing to how we usually will calculate the median. We put the number together and sort. Based on even or odd, the calculation of the median is slightly different. So that involves us to have a sorted sequence of the number. Since that nums1 and nums2 are already sorted, we can do the kind of a merging kind of a process to merge them into one sorted array, a longer one, in linear time, and then do a constant calculation, if-else condition to get the median. So that would be linear time. But this question asks something that's even faster than that. And the question gives us two sorted array. And to calculate median, it's usually good that we have sorted array. And the runtime requirement is log. So sorted array and log time. It's natural to think about we should try to use binary search on this problem. And the very last line here is just saying that they cannot be both empty. That means we have to have at least one element, so the median is always there. So that's this just a guarantee there. Some of the example, we have 1, 2, 3, all number of elements. So the median is the middle one. That's the number 2. The second example, we have 1, 2, 3, 4. So the it's odd. It's even number of elements. We take the average between the middle two elements, 3 and 2. So that's 2.5. That's these two examples. As for my purpose, I'm gonna use a little bit longer example. We're gonna start with numbers 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, baby sounds listen too much. So the median is gonna, in this case, is gonna be the middle between the two elements. Because we have 10 elements, we take the middle two, 5 and 6, add together and divide by 2. We get the median to be 5.5. And on the notion of a partition that this median value can create is that you will put 1 to 5 into the lower buckets. That's the number smaller than the median, smaller or equal to the median. And we have 6, 7, 8, 9, 10 to be on the other bucket where we have the numbers that's larger than or equal to the median value. So this is a big array. That's that you can imagine if we have the brute force solution. This is the merged version of the array. So unfortunately we don't have that. We are not allowed to actually do this merging to get this. What we will have is the splitted version of this array. So just for simplicity, we're gonna have the odd numbers together and even numbers together. So obviously we have this as the nums1 and nums2. We should return 5.5. The question is how we can efficiently get to the 5.5. We notice that this the notion of partition still exists even though that these two arrays are separate now. The 5.5 creates a partition number in between 5 and 7 in the first array, and it creates a partition, kind of a cutoff line there between 4 and 6. We notice that if we consider these two left-hand side added together, it's indeed to be able to recreate the original, 1, 2, 3, 4, 5 in the larger picture, the full picture kind of a view. The two right-hand side together, they recreates this 6, 7, 8, 9, 10. So one thing we can obviously do is to define this two cutoff points to be two options, like a P1, P2. That's on the surface might look like two options, but it's really just one. So let's say that the P1 is 3. That means we will have from you will cut the array into two halves, where the first half is nums 1 from 0 to 3. So it's the left-hand side is inclusive, right-hand side is exclusive. I'm gonna put P1 here, and the right-hand side is basically nums 1 from 3 and on. So that's the partition it creates with this P1 equal to 3. The P2 here is obviously 2. So now our problem now is basically try to figure out this 3 and 2 value, because these are the this recreates this original partition, and we can see that the numbers that we use to calculate the median, the 5 and 6, does live very close to this vertical line. One is on the left hand side to the first partition line. The other element is on the right hand side to this partition line. So if we can find this partition, it's guaranteed, this two partition line, it's guaranteed that the median value, it's either in there if we are working on the odd case, or if it's in the even case, we're going to be able to, it's one, they are the two of those values, two of those four values around this splitting line. That's the guarantee, because and to be more specific, what we can see here is that 5, the smaller among the two, the potentially smaller among the pair of median calculating numbers in the even case, it's going to be a larger one from the left hand, the two left hand side combined, and the other one is going to be the smaller one from the two right hand side together combined. The question is to we talk about a lot about if we do have this P1, 3 and P2 equal to 2, we will be able to find the median relatively easily based on some logics and enumerating over some possible cases. The problem is, how do we efficiently find P1 and P2? And it, on the surface, look like P1 and P2 are two separated, isolated choices, but it's actually not, because we know the total number is 10, so we know that the left-hand side has to have 5 numbers, right-hand side has to have 5 numbers. And if the P1, we just made a random guess, equal to 3, then P2 in the correct partition, it has to be 2. So we have this relationship here. So instead of making two choices, we can just try to pin down the P1 value. And it might not be obvious in this case here, but let's do some two other kind of options. We will be able to see how this is working out. Let's say that we made a wrong guess that P1 is equal to 2. So that leads us to have P3 equal to 3. So we are on the left hand side of the correct answer. So in that case, we find the larger among the left hand side is going to be 6, and the minimum from the right is the minimum between 5 and 8, which is 5. So we got this invariant there. That's not that's indicative of we have a wrong partition. So if we combine this together, we will basically kind of mistaken the order between 5 and 6 if we choose P1 equal to 2. So let's look at another case. This time we're gonna be on the upper side. So we're gonna have P1 random guess, maybe some guess from some heuristic equal to 4. In that case, we will have P2 to be 5 subtracted by 4, which is going to be 1. And in that case, we will do the similar left-hand side and right-hand side maximum minimum calculation. The maximum from the left is going to be 7. The minimum from the right is going to be 4. So we also have this invariant. I'm just going to put this line here. Sorry, it's the maximum from the left is smaller than or equal to the minimum from the right. So if we see this invariant, that means we find the wrong partition point. Then we need to figure out how can we move the guess towards the right direction, because these two they just tell us the order we're messing up the partition point. It doesn't tell us where we should move this. So then we should go back and look at those 4 numbers around those 2 separation lines. We noticed that here in the case 1 we have the maximum from left from the second array is larger than the minimum from the right of the first. That's a invariant, right? Yeah, that's our invariant, because in the perfect partition the left-hand stuff is never be larger than any right-hand side element. We find 6 is larger than 5, so that's telling us we should move this bar towards right, so that we'll move 5 towards the left and move the invariant move the 6, which is in the wrong place. It should be in the promoted to the upper bucket. So that's telling us we should increase the lower bound. And in the second case here, we notice that the maximum from the left of the first array is larger than the minimum from the right of the second array. That's also a invariant. The reason is just similar to the above, that the left-hand side elements should never be larger than the elements from the right-hand side. And if it's this case, we would want to move the bar towards left to have this larger value promoted to the upper bucket. So in that case, we want to decrease the upper bound. So now we see that based on this relationship among these 4 numbers, we should be able to figure out one, whether we have found the correct partition point. The second is partition location. The second is, if it's not in the correct partition point, to which direction we should continue the search. So that gives us the 2 conditions. Yeah, one is to identify, do we find the right number? The second is, if it's not the right number, should we go up or should we go down? So with this, we should be able to conduct a binary search on this problem. So just for time complexity benefits, we should we can, if let's imagine the nums1 and nums2 are of different lengths, we should swap them to have the nums1 to be smaller, so that the search space can be a little bit small. But that doesn't really matter that much. A couple of boundary case I think we should consider. before we talk about the odd case, because now the question we have right now is just an even number of cases. So we're just going to talk about one boundary case. Let's say that P1 is actually equal to 0, so it's effectively here. Then the left-hand side has nothing. And actually this case can contain two boundary cases. So if we take the maximum from the left, this is nothing. What number should we put? We want to use 10 as the maximum of the the left-hand side. So if P1 is equal to 0, we will use interminimum as the maximum left of the first array. And for this case here, the right-hand side of the second array that after in this kind of special partition has nothing. So the minimum number, what should it be? It should be the intermaximum, so that we're gonna always use the other minimum number from the right-hand side of the other array. So that's just how we handle boundary case. If it's 0, we're gonna take minimum, interminimum. If it's the end, meaning you don't have nothing, you have nothing from the right-hand side, you will use intermaximum. So that's how we deal with the boundary case. The only thing that's left is how we, in what case, in the case that we have a odd number of cases. So let's say that we remove the number 10. We will have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number 5 is by itself is the median value. We have these two sorted subarrays. Similarly, it's just for the second array we don't have that. So P1, the partition point is going to be between 4 and 6, and for this one, the middle value, the half of the elements is, let's actually do 5, so that we make the it's a decision we should make, whether we include the median to the left-hand side or the right-hand side if it's in the odd case. Then for this halves calculation, we're just gonna basically do 9, divide by 2, and take the ceiling, so that the partition point looks like this in the two separate splitted arrays. Then we find that the correct median is going to be, if we do take the ceiling, median is going to be the max from the left. So that's how we handle the case when we have odd number of numbers in these two sorted arrays. So that's pretty much the walkthrough about how to reason about how to solve this in binary search, how to come up with this relationship, to criterion to determine whether we find the correct partition, and if it's not the right partition, how do we move forward to reduce the search space. Here is how we handle the edge case when the partition puts nothing on one of the sides. And very lastly is if we have odd number of cases, how do we figure out the median number. That's tied, the logic's tied up to how we actually calculate the half in the odd number of cases. If we take ceiling, it will be the maximum from the left-hand side. I think if we take a floor, it will be the minimum from the right-hand side. The two right-hand side combined, we take the minimum. That would be the median in the odd number of cases. So with that out of the way, I'm just gonna code this up really relatively quick. So gonna grab the number of elements from those two arrays. We're gonna use this to determine the case when we determine the boundary case and detect the boundary case, and also to use this to calculate the median, the half. Sorry. And then it's the half, the notion of half, 5 elements on the left and 5 elements on the right. In our explanation decision here, we choose to use ceiling, so it's effectively these two numbers add together and divide by 2. You know, this is taking floor, and we're gonna have a flag that tells us we have even number or odd number of elements in the array. That's affecting how we do this median number extraction after we terminate it in the binary search. So it's these two added together, do an AND operator with the 1 bit. So if it's odd, it will definitely have a 1 bit. So we do an AND with 1, it will tell us whether it contains odd number of elements. So that's some initialization of stuff. Of course, for the binary search, we're gonna have L1, the lower bound to be 0 and the upper bound to be the N1. So as we said, to make the search space slightly smaller, we can try to swap these two arrays to have the smaller one be L1, so that we perform binary search on the smaller one. So that's essentially. If nums1 is longer, we will do this swap. So that's this. We are swapping the reference right here. Yeah. Then it's the binary search. Since that we are finding a correct partition number, it's the smaller than or equal to termination criteria here. Then is going to be the P1 and P2 calculation. P1 is going to be the median, the M value between low and high. Your usual way of calculating the middle pivot number. And P2 is going to be half subtract the P1. And then we're just going to grab those 4 numbers around those 2 separation lines, partition line. Max left from the first array is going to be, if it's the boundary case, that means that P1 is 0. If it's not that case, we're just going to be the element P1 subtract by 1. You know, since that we have P1 equal to 3, this index is 2, so it's P1 subtracted by 1. That's the index for the maximum from this first array, and P1 itself here will be the minimum from this from the right hand side for this first subarray. So that's this, and what's the decision for the boundary case? If it's indeed 0, we're gonna use int minimum, so that when we do the max between, just gonna put it here. So that if it's int minimum, that one is well defined. It has to be. We will just take that and ignore this one. So that's that. For 2, it's similar. We just change 1 to 2 basically. For the right hand side, it's similar. Minimum from right of the first array is going to be, the boundary case is when we have the P1, the partition point to be at the end of the array. So that's P1 equal to N1. If that's the case, we would do If that's the case, we will take, what's the decision? Int maximum. Otherwise, we're just gonna grab that value. You know what? I'm just gonna change the order so that it align a little bit better. So the normal case and the abnormal case. So less than, it's not equal is basically less than in our case. And for the second array, we do the same thing, just changing 1 to 2. And obviously we need to take the minimum from the right hand side, two right hand side combined. Oh, no. So with these numbers in hand, we should be able to start to calculating this. We want to test has the binary search find the solution, find us the correct partition line or not. That's taking this. If this is the case, that means we have successfully find the correct partitions. What we need to do now is to, if the case is odd, we should return the maximum from the left. Otherwise, we would return the average between these two. So that the maximum from the left and the minimum from the right. We take the average to get that case, to return that. Do I need to? Yeah, I need to convert this to double myself. Yeah. So that we are returning double, right? Yeah. Okay. So that's when we actually find the correct partition number position. If it's not the case, we should, based on this two formula here, to increase lower bound or decrease upper bound. So the thing, I'm just gonna copy this for increasing lower bound. If it's this case, we're gonna do what? Increase the lower bound, right? Increase the lower bound, okay. The other case is this. We will decrease the upper bound. So yeah, so that's pretty much it. That's the binary search solution, I think. Let me just quickly check to see if I have obviously problems. We swap these two arrays to make sure that nums1 is always going to be the shorter one, because we apply binary search on this one to save slightly a little bit small time. Num1 is the size, n2 is the size of the second one. Half is calculated as this two. Oh, I should plus 1. Because this one is floor, so if we have 11 elements, it will be 5, so that it's not ceiling. So if I add 1, it will be actually doing the ceiling operation. So it's 11 plus 1 is 12. 12 divided by 2 is 6. So in the case we have 11 elements, we're going to take the 6 as the median. So the median, since it's 6, and the left-hand side by this half calculation is guaranteed to have 6 numbers, so it's going to be the maximum from the left. So that's why we can return max left in the case of all number of elements. Here we detect whether the number is even or odd by doing this. This is now our initial search space, and the termination has an equal sign because there are this point where we actually find this number, and since we contain equal sign, the updates can be strictly larger or strictly smaller than. Then is the maximum from the two sides. Depends on whether we on the boundary case to have nothing from the left. If we do have stuff, we use that stuff. If we don't have, we take minimum. The right hand side is a similar story. If we still have stuff on the right hand side, we choose the first one that's going to be the minimum. Otherwise, we just say we don't have anything. We are maximum. Just use whatever you have. So this seems okay. Then we take the maximum from the left, we take the minimum from the right. The relationship between these two is telling us whether we find the correct partition or not. If we do find the, if this turns out to be true, that means the P1 and P2 is correctly partitioned these two subarrays into two halves. Where we combine them, they recreates the bigger kind of picture partition. Based on the even and odd case, we return things differently. If it's odd, we return the maximum from the left. If it's even, we take the average between these two middle elements. And then it's just if you still haven't find it, then this is now a updating rule for the lower bound and upper bound change. So I'm just going to return -1 here to be a little bit safer. Let's see if it works. Okay. What's the problem? Typo. All right, let's see if it works. Okay. Yeah. So that's the binary search. I think it. It should be clear. It should be clear. It's not an easy level question. A little bit anecdote about this question. I got this question like 3 years ago, interviewing for junior level, entry level data scientist job, and I got a bar riser round where we have a team lead from the data engineering team, and he threw me this question. I totally screwed up. I just haven't prepared that much for algorithm questions because I'm interviewing for a data scientist question role. So yeah, quite embarrassing. So after that, I go back and pick up the book about algorithm, looked at that for like 5 minutes and say, you know what? Unless I find in my job I really need to write a lot of software code, otherwise I wouldn't be looking into those type of questions. If the role require that, I will skip. But it's funny that throughout the past 3 years, I began to do more and more coding stuff, more and more software stuff, and find this to be actually helpful to have you to think about questions systematically. And yeah, so data science is still software code, no matter it's analytics or modeling. It's software code, and to have solid knowledge here is definitely a plus. So yeah, a little bit off topic. So that's for this question today.